Hello and welcome to the final video of this course. And in the last tutorial we discussed the left hand side and the right hand side derivation for the pressure Poisson equation using the momentum equations. And just to let you know that there is a slight mistake, because here the dou v by dou y squared term is correct, and this term I have apparently changed it in writing. It should be dou u by dou x squared plus this term. So now we have our correct form of equations, which we will be using in the pressure Poisson matrix. And just 1 second. So now we've got everything correctly, and we said that the divergence terms can be approximated to the value of 0, and therefore we come up with the final outcome of the equation. Now this is obviously only true in a continuous kind of mathematical domain, but in the numerical domain the divergence term, even if we enforce the divergence free conditions, the divergence terms is not absolutely 0. So one way of tackling this problem is to keep this term retained in the pressure Poisson equation. So you will know what I'm talking about when we go to the final equations for the 2D lid driven cavity. And let's start our understanding. So we got the 2D lid driven cavity, where I've actually rotated the domain just to make it consistent with C++ matrix notations. So I is the row and J is the columns again, and I starts from 0 and ends at nx minus 1, and this is called the inlet boundary condition. So at the inlet we have a value of 1.0 for the u velocity. So for the u velocity we've got a 1.0, and v is 0 and p is 0. Everywhere else u and v are 0, and p is known as a zero gradient boundary condition. So we apply a zero gradient boundary conditions for p at left outlet, or you can call it bottom, and the right. So let's go ahead. We've got our u momentum equation, our v momentum equation, and our pressure Poisson equation with a source term. We said that the source term, we derived the source term. However, yeah, we'll come to that in a bit. Let's tackle the u momentum equation first. So nothing is changing here. I'm just rearranging to make this new velocity to be the subject. So these two guys that represents the convection terms are plus on the left hand side, but when we take them to the right hand side they become negative terms. The pressure gradient is already a negative term, and so we've got everything on the right hand side now. And when we discretize the time derivative term, this is what we have: uij at n plus 1 minus uij at n, and we can take this delta t to the right hand side and multiply everything there. And because this term is a minus term, negative term, when we take it to the right hand side it will become a positive term, so it should be added to the right hand side, and then we can get the new velocities from there. So moving on, v momentum is similar. Just take the convection terms to the right hand side and make vij n plus 1 the subject. Spend some time or try to rearrange them by yourself to make it more clear. Now we move on to the pressure Poisson term. So obviously this is what we saw before: minus rho multiplied by these three terms, the last three terms. Now I am adding another term here which is called the divergence term. So the divergence term for the time, the change of velocity. So what we do is we write this exact function as it is and multiply it with 1 over delta t. So the pressure Poisson discretization is not something that's not familiar for us. We did this before in couple of tutorials before. I think it was the Laplace equation and the pressure Poisson equation with a singular source term, and just the B source term is replaced with rho multiplied by, because it's a minus, so when you multiply the terms they become automatically negative terms, so everything is negative in here, and then we take the common denominator. So if this is confusing, let's look at the Poisson equation one more time. So we have this particular, because here the B can be any source term, and we used a value of minus 100 and plus 100, and that source term is multiplied with dx square dy square and subtracted from the left hand side parts. So a similar kind of thing happening here as well, just that the source term is a bit more complex. So if you think of this particular rho multiplied by this entire term in the bracket, which is actually B, so it's the source term, nothing else is changing. Okay, so now that we have discussed the discretizations and the rearrangement of the equations, let's move on to the coding part. So we've got everything that we need except that let's look at the code and we will discuss. So in the finite difference separations, we already wrote the gradient of x, gradient of y, the Laplacian of x and the Laplacian of y. Now we have to write another two terms which also determines the gradient, but the gradient with central difference approximation. This is what we need. So it's quite simple, and we need this to for these terms. The pressure gradient has to be discretized using central method, and also these terms that appear in the source values for the pressure Poisson equation has to be discretized using the central difference approximation. So dou u by dou x multiplied by dou u by dou x and dou u by dou y, all these terms we have to take central difference gradient. So we can, there's absolutely nothing complicated here in writing this central difference. We just copy paste and just say that the I plus 1 minus I minus 1. So central difference is if you have, for example, if you have grid points which is looking something like, let's say x are the grid points, then from the method that we used initially, let's say grid x, we take, for example, if this is I equal to 0, then this is I equal to 1, then this is I equal to 2, and this is I equal to 3. Then we say that the grade x will be, for example, at this point will be the value, for example, u velocity at I, which is 1, minus u at I minus 1, which is 0. In central difference, we say that the gradient will be the I plus 1, which is 2, minus I minus 1, which is 0, divided by 2 times dx. Okay, so how do we get this 2 times that term correctly? It's quite simple. Just one way is to just say that I plus 1 minus I minus 1. So therefore we have dx multiplied twice, or dx plus dx. Another way is to just multiply this term by 2 itself. So let's use the I plus 1 method for now, because we are only calculating in the internal field, starting from I equal 1 ending at I minus 1, size minus 1. So we won't be going out of scope or out of the size of the vector, because we say, for example, if we had a vector size of 15 or 16 by 16, then the least possible in I direction we can go is 1 minus 1, which is 0. So when we start from 1, we can't go out of the vector size in the beginning of the vector. And when we end at minus 1, then even if we take a value from I plus 1, we will still reach the maximum size. So we will never go out of scope. Okay, so let's say now that our gradient x is written. Let's write the gradient y term. So gradient y CDS will be j plus 1, j minus 1, j plus 1, j minus 1. So simple as that. We've written gradient x CDS and gradient y CDS. We also wrote the Laplacian x and Laplacian y, and we also wrote the Lep op term in one of the tutorials. And if we look at our pressure Poisson equation, then we know, let's actually go to a simpler version. We know that there's always a denominator, which is 2 dx squared plus 2 times dx squared plus dy squared, and the term which is taking the I values has to be multiplied by dy squared, and the terms which takes the j values or j direction has to be multiplied by dx squared, and the source term has to be multiplied by the product of dx squared and dy squared, because it's on the right hand side. So we could easily split this into 2 parts as well if we wanted to do that. There's no harm in having it in one go as well. So I went ahead and wrote the separate x and y components of this Laplace operator. So the x component is nothing but the value at I plus 1 plus the value at I minus 1 multiplied by y. So the value at I plus 1 minus the value at it should be a plus here, so this is my mistake. Should be a value of plus, right? Okay, so the value at I plus 1 plus the value at I minus 1. So here we go, the value at I plus 1j plus the value at I minus 1j multiplied by square of y, so multiplied by dy squared, divided by the denominator. And what is the denominator? The denominator is 2 times spacing square x plus spacing square y. In the presentation it is called dx square plus dy square. And similarly we can do for the y term as well, or Poisson y, and this will be this particular thing on the numerator. So j plus 1 plus j minus 1. So we have got here vec I j plus 1 dot value plus vec I j minus 1 dot value multiplied by dx squared. So multiplied by dx squared and divided by the denominator. So we've got our Poisson x and Poisson y term in case we ever need it. Okay, so let's go and start writing the code for the lid driven cavity. One other thing I did is everything that we have seen before, starting from creating the mesh using n rows and columns, length x and length y, and we pass it to the mesh constructor. We create a object of fields class as well, and we create some fields. So we did this before, u, v, p, un, and we pass the grid information. And where's that? We create the solution object as well, and we did the boundary names. And now I'm saying that just to give some values, because we discussed this in the presentation, it shouldn't be unfamiliar. We said that the velocity at the inlet is equal to a value of 1.0. So I am just writing ahead that a second, that the u lid is equal to 1.0. And now to make things easier in coding, I'm obtaining some information from the mesh so that I don't have to write everything using the objects. So I'm saying that the double dx is equal to the mesh object dx, double dy is equal to the mesh object dot dy, and the spacing square is dx multiplied by dx, spacing square dy is dy multiplied by dy, and this guy here, b spacing, is coming from, so when we write the pressure Poisson equation, we need to multiply the source term with dx square dy square divided by dx 2 times dx square plus dy square. So I'm writing the dx square multiplied by dy square divided by 2 times of dx square plus dy square. So this is numerator, this is the denominator. And to be honest, this is not necessary. Also, when we introduce the pressure gradient term to the momentum equation, we need to multiply it with some negative terms, for example convection, and also we've got here with the pressure term, we got to multiply it with 1 over density. So I'm saying that inverse rho is 1 over density, and r delta, which is needed in the pressure Poisson equation, because I said we will multiply the divergence with 1 over delta t. So 1 r delta t, actually let's call it r delta t, or leave it as r delta, is just simply the solution time step size. So 1 over 0 divided by the solution time step size, and b spacing rho is this guy multiplied by the density. Okay, so b spacing rho is needed for the pressure Poisson equation. It's just simply b spacing multiplied by the density value. And also in the pressure Poisson equation, we need to multiply this particular term with a 2. So I'm writing 2.0 as 2 and 0 value as we could say 0.0. I just wrote it as a very small value. Okay, so now we can start writing the lid driven cavity a solution. Okay, so um, I've also included some solution parameters saying that the solution will run for 1000 time steps, and it will be at the delta t value of 0.002, and the density will be simply 1.0, and the viscosity will be 0.1, and in every time step there will be 50 inner iterations, and in these inner iterations we will try to converge the pressure Poisson equation to a target residual. If it is not converged in 50, move on to the next time step. And yeah, that's it. So first of all, let's see what kind of fields we have that we have created. So in create fields, I created UVP and UNV and PN, the new ones, and also a extra field called B, which is representing the source term. So this is the source term for the pressure Poisson equation. First, let's decrease the grid size to something like 10 to make it easier for us to visualize. So let's call the object of the fields class and initialize a boundary condition at the inlet with the value of ulid. And after having done that, let's print out the field to see if everything is okay and if it is as we want it to be. Right, let's comment out this write file for now, and let's print the vector u. And it then run. Okay, so this is our inlet with the velocity of 1, and everywhere else it is 0, and this is the only boundary condition we need with outside the time loop. So next, let's create the time loop. Basically, since we have declared some variables here, we can use that. So for nt, which is the this should be nt max, it's the maximum time steps it can run. So let's say for iterations is equal to 0 to iterations is less than nt max, then it plus plus, so iterate, and this will be our main time loop. Main time loop ends here. The first thing that we need to do is to say that we want to pass the old velocities is equal, the new velocity is equal the old velocities, and un is equal to u and vn is equal to v. And next we have a pressure Poisson calculation loop, inner iterations. So let's write a comment here, inner iterations begins here. Right, so for nit equal 0, so n inner iterations equal to 0 to nit is less than nit max, then iterate. So as long as it's less than 50, iterate, and within this time loop we want to pass that Pn is equal to P. So we have already passed our old velocities. We have initialized the new velocities from the old velocities. Okay, so next comes the pressure Poisson equation. Since the equation is a bit complicated itself, let's first write the source term. Let's go ahead and have a look at the source term. So the source term is simply this guy here. So I said that everything in the source term has to be discretized with a central difference gradient, and this is the divergence term. So let's start writing it. So the source term, we created a field for that. It's called B. So let's say that B is equal to, first let's write the divergence term, which is R delta, or 1 over delta T. So R delta is equal to 1 over delta T, which I can show you again from here. So R delta is 1 over delta T multiplied by FD grad X CDS of U plus FD grad X CD grad Y CDS plus FD grad Y CDS of don't know why it is happening like that. So grad Y CDS of U. Okay, so that's the first part, minus, let's put this in a bracket, FD grad X CDS of U. So now we are writing this term. So dou U by dou X multiplied by dou U by dou X. So grad X of CDS U, and then, which means multiply grad X CDS of U. Now moving on to the next term, FD, this time this is grad Y of U and grad X of V. So gradient Y CDS of U, and then FD grad X CDS of V, minus, then we write the this term has to be multiplied with the 2 itself, so minus 2.0 times, or actually we wrote 2 in the create grid and solution header file. We wrote a 2, so 2 times this term minus FD, this time we go for the V velocity V, and then FD grad Y CDS, so multiplied by itself. Then we close this. There we go, we have written our source term. Now let's call the equation. Let's go ahead with the equations. So equations class, and we call this the pressure equation, and put the constructor, close it. And now if you look at this is the pressure. Of course, this divided by the denominator is the Poisson X term, and then we have to add to that Poisson Y term. So we could call FD Poisson X of P n plus FD Poison. Sometimes it comes up, sometimes it doesn't. Of pn minus. Now we have written the entire source term, but we need to multiply the source term with this dx square dy square divided by this, and also with rho. So we multiply with b space in rho multiplied by b, and that's it. We have written the pressure equation without much hard work. So now we need to say that for the entire size of the vector, so from I equals 0 to I is less than p dot size I plus plus, then just we'll get practice of writing this kind of loops. So there we go, we have written the entire thing for in j, j and j, and we know that if we write j, this has to be called with I, and we will say that pi j dot value will be equal to the pressure equation dot equation field ij dot value. Okay, so this particular part is passing the values to p. Our job here is done. Now we move on to the boundary conditions of the pressure. So we said inlet is fixed value, everything, or not everything, maybe all other boundaries are zero gradient. So field upper dot fixed value boundary and p inlet and zero value. Field upper dot zero gradient boundary conditions for p, outlet field upper dot zero gradient boundary conditions for p right, and field upper dot zero gradient boundary conditions for p left, and we are done there. Now we need to calculate. Remember that we wrote an equation, not equation, a double value called L1 normal. So we can say that L1 normal is equal to field upper dot L1 norm of P. Let's actually, I forget now exactly what order it has to be passed. So let's check. Right, so we are L1 norm. New has to be passed first and old later. So P and PM, because here the new is what we calculated most recently and old is what we started the loop with. So P and PN there. Right, so now let's write an if loop. If L1 normal is less than our target residual, then CR pressure equation is converged, and end line, and then break from this for loop. So if not, C out. So now we are outside the loop, so the loop starts from here, ends here, so this is the end of in inner iterations loop for pressure, and then we say cout pressure equation residual, let's call it residual, and then L1 normal and end the line. Okay, so now we have written our pressure equation. Time for us to write our momentum equations, and they probably will be simpler. So U equation, constructor, close, and let's have a look at the presentation. We want to write it exactly as it is. So let's first write this term. So we can start with the convection part, and we actually need to say that the first term is minus 1. So I don't need to write the minus sign. So minus 1 multiplied by U and U multiplied by FD grade X of U, and then minus the second term, which is V multiplied by FD grade Y of U. So convection terms are written now, minus so the pressure term is simply minus 1 over P of dou P by dou X. So minus 1 over rho of dou P by dou X. So have we written a term for minus 1 over rho? We have actually a term called inverse rho, and that means we can write in minus in rho, which is nothing but 1 divided by density, so minus 1 divided by density multiplied by FD grade X CDS of P, my bad, here we have to actually, because we have obtained a new field, we have to take UN here, everything with the new velocities, but pressure remains the same, and that's the pressure term. Now we have to add the diffusion term, because the diffusion term holds a plus sign. So the diffusion term is simply solution dot viscosity multiplied by FD Laplacian of U and plus FD Laplacian Y of UN and close the brackets. So let's see, we've got our two convection terms with negative signs, pressure term with negative sign, and this term with positive sign. So the one thing that is missing is a bracket here. So this term is closed with these brackets, this term is closed, this term is closed, and this term is closed, and the equation constructor is closed successfully, and we have written the entire equation. Now it's time for us to say that multiply whatever is the outcome of the equation with delta t and add the old velocities. So simply u will be equal to un plus delta t times, or let's actually say solution dot delta t times u equation dot equation field. Okay, so there we go. Then we called for the boundary conditions. So field upper dot fixed value boundary u inlet and value of u lid. Everywhere else 0 value. So field of fixed value boundary u outlet 0 value. And let's just copy this 2 more times. Oh, right. So we copied it. Now only we need to change the name of the boundary. So left and right. Okay, so our u momentum equation is done at this stage, and we can copy the entire thing and write the v momentum equation easily, because the only term that the only terms that are changing is the gradient should be taken with respect to v velocity, and the gradient of pressure will be taken in y direction, and the Laplacian will be taken with v velocity. So simple as that. And the outcome will be v plus vn plus delta t times v equation dot equation field, and boundary conditions will be almost the same, except the inlet will also hold the 0 value. So there we go, we return the entire thing. Okay, so we are done, and what we need to do is just write the file whenever we want. So we will write it every we will write it every 100 time steps, and let's see if this time is being passed. So in the for loop we can say that because we created an integer called time, I hope that we did, we actually haven't, so let's create another integer saying this is time equal to 0, and then let's say that time will be equal to iterations, and let's also print out iteration number and it, and then end the line there. And now time is being updated and we can pass this time. So let's build the project and let's see if there's any errors. Build again. Right, because of this ntmax, and then build again. Right, this should be called an integer because we didn't declare it before. So int it equal to 0. Here I made a silly mistake. Let's go ahead debugging, and here this also hasn't been declared yet, so integer. Okay, so everything works fine now. It's all compiled. Now it's time for us to check if everything is okay. Then we could, yeah, let's run it. Just to check, double check how many elements are there. So 20 and 20, so 400. Build and run, and so it starts with residual 20 and it's increasing and going the other way around. So we quit that, and it looks like that I just reduced the time step size to a more reasonable value and viscosity, and we will write the file at every 100 time steps. For now we will start with a grid of 20 by 20, but I will run the final solution with 50 by 50, and now also the residual starting with 20, but now with smaller time step it's more stable. And as the grid density increases, you need to reduce the time step to make sure that the convergence is achieved. So as you can see, the pressure equation residual is dropping, so I'm not going to run it for the entire time as my laptop is full of too much stuff and it's a bit slow. So finally what I'll do is I will run this for a 50 by 50 grid, and I will show you the solution, what it looks like for this particular run, by opening ParaView. um, and I have opened the ParaView, and the one I ran for the 50 by 50 grid is in the build debug bin, and I've placed it in a folder called 2D lid, and this is our solution. So let's have a look and change the color to something more colorful so we can visualize what is happening. So this is the north side or the inlet velocity, and you can see the development of the u velocity field as time goes on. And if you decrease the number of table values to something like 48, you can more clearly see the kind of contours. And let's have a look at the v velocity field and apply, and let's again reduce this to 48, and we've got the v velocity contours and the pressure as well. And this time we will use again rainbow with maybe 25, and we can see the pressure field as well. Okay, so that should be the end of this course, and I hope you enjoyed it. I've already written coded and tested the finite volume method using simple algorithm for in C++ object-oriented methods, and it seems it probably will be a bit more complex than all of this, but should be an enjoyable course, and I hope I get to upload that soon as well. And thank you for doing this course. Right, good luck.